All right, today we're going to start Chapter 4, Section 4.1. We're going to look at exponential functions and their applications. So I'd like to remind you of a few details about exponents. These are things that we've seen before, but we're going to make use of them very regularly in what we're doing. So when we have a negative exponent, what I want you to remember is that negative exponents actually move locations. So if the 3 is sort of in the numerator, like this is like 3 to the negative 2 over 1, it moves down to the denominator, and that power that was a negative 2 is now a positive 2. Okay, so if you move move an exponent with a power up or down, it changes positive versus negative. And what is 3 squared? 9. So this is 1/9. Does anybody remember what it is when you raise to the power of 0? 1. That's 1. Now the negative on the outside here is still there. So this is a negative, and then it's a number 1. So this is actually negative 1. Okay. What would it look like if it was all raised to the power of 0? You'd actually have parentheses like this, but there aren't parentheses like this here. So it's not negative 4 raised to the power of 0. It's just 4 raised to the power of 0, and then a negative on the outside. Okay. When you actually have a fraction and it's raised to a power that's negative, you can actually flip the fraction upside down. And so we can write this as 3 over 2. And now my exponent's positive, right, because I flipped my fraction. It applies to the top and to the bottom. So this is 3 to the 4th over 2 to the 4th. I should be writing in white. I'll change that in the next one. What is 3 to the 4th? 81. And what is 2 to the 4th? 16. Good job. So 81 over 16. Fabulous. Okay, good so far? Awesome. Exponential functions look like this. They look like f of x. We are dealing with a function. And it's a base, this value a, raised to the power of x. The a is positive. Okay, it could have a negative out in front, kind of like this number 2 did, right? But the exponent itself, x, applies only to the value that's positive. And it can't be 1. So it could be a fraction, like 1/2. It could be a larger number, like 7, or 152,493. Right? It could be any of those, but it can't be 1. Now, when we're looking at the domain for an exponential function, we'll look at the graph here in a moment. Domain means x values. What x values can I plug into this? So if it helps you for the moment, just pretend you have the number 2 like this, just so that you have sort of a visual reference point. X values. Well, clearly x can be positive. No problem, right? 2 to a power, no big deal. X can also be negative, because I just would flip it upside down, right? And x can be 0, because 2 to the 0 power would be 1. We've explored pretty much all our options. My domain is negative infinity to infinity. It can be anything. The inputs can be anything. However, when I take a number that's positive and I raise it to a power, I always get a positive number. Kind of like when I'm working with absolute values or square roots or something like that, right? I always get positive values out of this. So my range is actually 0 to infinity. And I can't get 0, so there's the open parenthesis, if you will, next to it. I can't actually ever be 0. It is really positive. Okay, you ready to look at a couple different graphs? Yeah. There are 2 distinctly different graphs that can occur for exponential functions. One of them happens when that a value is bigger than 1. And again, just for an example, if you want to think about it, we could think about y equals 2 to the x. Okay? And if you have that as your equation, the graph looks like this. And in particular, right here, this location where it crosses is at 0, 1. So it's got a y-intercept of 1. Okay. The other option is that you have those fractional values between 0 and 1. And again, if you want to reference, like what might that look like, you could have something like y equals 1/2 to the x, okay? It's the same thing, it's just 1/2 instead of 2, right? I'm going to run into space problems, so I'm going to move this down. It still crosses at 0, 1, but it actually is a declining or a decreasing graph now instead, like this. And it's crossing, like I said, at 0, 1. That's what I wrote in as an example, yeah. Anything between 0 and 1 is what we want there. So in both cases, we made mention of the y-intercept. The y-intercept is at 0, 1. That's the same thing on both graphs. And the reality is it's also got the same horizontal asymptote. So asymptotes you learned about without me. Well, I mean with me, but from a distance, right? So asymptotes are these lines that you get really close to and don't touch. Can you tell me what is acting as an asymptote in both these graphs? The x-axis is, right? In both graphs, either on the left side or the right side, one side or the other, the graph gets really close to the x-axis. Agreed? Yeah. So the x-axis is acting as a horizontal asymptote. And the equation for the x-axis is y equals 0. So these graphs are always going to have a horizontal asymptote as a part of the graphs. But that horizontal asymptote could be shifted up or down. And we know how to shift graphs because we explored that in chapter 3. So we're going to do some examples now that have some shifting of these ideas going on. You ready to take a look? All right, here's our first example. It's 3 raised to the negative x plus 1. So we need to talk about what's going on with these different reflections. And I think it might have been in chapter 2 now that I'm thinking about it. Was it chapter 2 that we did all of our shifting? Yeah. I think that was on the test that I graded, so I think it's chapter 2. Okay, cool. All right, so when you have addition of a value at the end or subtraction, it shifts it up or down. That's what happens. So do you remember, does addition shift up or does addition shift down? It shifts up. So this graph is going to be shifted up 1. So I'm just going to make a couple of notes before I try to draw anything. It's going to shift everything up 1. Now, there's a negative that's inside here with this x. Well, when I make negatives or when I include negatives either in the very front of something or inside with the x, it reflects things. It either reflects them down like this or it reflects them over like this. Do you remember what the negative on the inside, how it reflects? Does it reflect over y or does it reflect over x? Say it loud for me, Megan. It reflects over y. So this reflects over y. And if you have a hard time remembering which is which, this is actually a horizontal reflection. And anything that occurs inside happens horizontally. Anything that occurs on the outside happens vertically. Okay? So this is a horizontal reflection. All right. So let's think about what this graph is doing. I want to draw just the basic graph that we had to start with, and then we're going to draw some shifting to it. So you may or may not want to draw my original graph. It's your choice. My original graph, though, looks like this, right? I'm supposed to take that graph then and shift it up 1. Well, that's simple enough. So I could actually take that graph and I could actually move it up 1, but notice if I do that, I previously had a horizontal asymptote at y equals 0, and now I'm going to have a horizontal asymptote at what? Yeah, at y equal 1. So this is where my new horizontal asymptote is going to be. So I can physically shift the up 1 part, that's fine, on my screen. I can't do the next part though. The next part needs to take the graph and to rotate it over the y-axis, right? So instead of it looking like this, it's going to end up looking like this. That's not a very good thing at the end. It needs to look like it's actually tapering down. That's better. So this is my actual graph. okay? That white one is sort of an intermediate step of what I was doing. It was my shifting up one step, but I need a reflection step as well.
What about the 3?
Okay, so the 3, what does the 3 do? Because we kind of sort of blanket statement said, hey, we can think about this like a 2 and like a 1/2, right? It actually affects how steep it is. That's really what it does. So if you were plotting points over here, which I'm not necessarily asking you to plot points, but this graph with the 3 to the x would be a little bit steeper than the graph with the 2 to the x. And in particular, what would happen, actually, let me go over here and I can show you what on this graph, the first one, is that at the value of 1, I should be at a value of 2. This should be at the point 1, 2. If I were doing it on my graph with the 3 to the x, it'd be at 1, 3. So we're not super interested in plotting a whole bunch of extra points. We're interested in plotting the shape, okay? The shape. We're interested in plotting the horizontal asymptote and the y-intercept, or where the y-intercept has moved to, like if there's a shift going on left, right, up, and down. Those are the features that we're going to be most interested in plotting. But if, for instance, my math lab wanted you to plot a second point or whatever, that's what it's doing. It's going to be using that value and going up an additional shift from there using that value, in this case 3. Okay, we already talked about our horizontal asymptote. We said that it's at y equal 1, so I can fill that in. Where is my y-intercept now? What was it, 0 what? 0, 2, exactly. It was at 0, 1 and it shifted up, so now it's at 0, 2. So I didn't plot it, but I probably should label it. It's at 0, 2 that it's crossing. And notice when I reflect it, it doesn't change, right? It's a stationary point on that y-axis, so it doesn't actually move. What's my domain? Yeah, domain doesn't change, right? Shifting and all that kind of stuff does not affect my domain. It does affect my range, though. What's my range? Yeah, my range is now 1 to infinity. Damaris.
I'm just still confused on how, when you look at the original equation, you know what the graph is going to look like.
Do you mean like over here?
Yeah.
You could plot points to justify it if that helps you to think about it. If you were to plot the points, there's 3 points in particular that would be helpful for graphing, -1, 0, and 1, which are points that we've seen plotted before in the early part of chapter 2. So if you plugged in -1, and we'll just use this equation right here. If you plugged in -1, you'd have 2 to the -1, which is 1/2. You'd have 2 to the 0, which is, sorry about that, 1, and 2 to the 1, which is 2. And if you were to plot those points, you would see that they fall like this. This should be at 1/2 height. And the thing happens, the same thing happens if I were to get things larger. Like, let's say I raise it to the power -4. Well, 2 to the -4 is 1 over 2 to the 4th. It's still positive, but it's really small. It gets really, really close to the x-axis on the left. If I raise 2 to the +4th, I get 16. It gets really big really quickly. So you've probably heard the phrase before, something multiplying exponentially. Have you heard that phrase? Yeah, this is what it's talking about. It gets really big really quick, okay? Multiplying exponentially. This is actually what people were anticipating with COVID case counts early on. We're multiplying exponentially. It didn't work out like that. Things have happened modeling-wise far differently than they were predicting for lots of reasons. But exponential growth was one original concern with COVID cases. So. All right, let's take a look at another one, and maybe I'll plot some points, Damaris, too, so you can see why it's happening the way it is, okay? All right, so this one has a little bit more going on. Well, maybe not more, but it's different. I still have a base of 3, but I have x minus 1, and I have a -4 at the end. Let's start with the value at the end. What is the -4 at the end going to do to my graph? Right, it's going to move it down 4. What's this -1 right here going to do? It will. It'll move it right 1. Everything happening inside with x sort of does the opposite of what we would expect. Look, it's sun shining outside. That's good news right there. Okay, so we're expecting to move this right 1 and down 4, correct? let's start with the down 4, because moving it down 4 means I move that asymptote down 4 as well, right? It's often easier to actually plot the asymptote as a reference point because we know what's going to happen nearby it. So here's down 4, and here's my asymptote now. I'm going to move it. Hang on. My screen a little bit bigger. Okay, so there's my asymptote, right? It shifted down 4, so my horizontal asymptote is now at y equal -4. Now, it's a very strange kind of question on the y-intercept one. Let's actually just plot the graph first, and then we will figure out the y-intercept from the actual equation. I'm supposed to move the whole graph down 4, which means that the graph should look like this. Agreed? But it's supposed to also move right 1. So if I take this graph and I shift it right 1, it hardly looks like it changes. Do you guys see that? And of course, I haven't drawn it near as steep as it probably should be drawn and so forth. But what happened was that that point, which was previously along the y-axis at -3 here, is now, should be right here. My graph is not very good. Let me see if I can draw it more convincingly. This is what happens when you're sketching, is that the graphs don't always look convincingly like they're supposed to be. How about that? So we're crossing at the point that's like shifted now. So this point now, instead of being at 0, -3, is at 1, -3. Because it moved it right 1. Now that doesn't answer the question of what's the horizontal asymptote. I mean, not horizontal asymptote, y-intercept. So we're going to have to go back to the y-intercept part to actually figure that out. A y-intercept, if you'll remember, is the location when x equals 0, right? So we're going to have to figure that out from our equation. So this is 3 times 0 minus 1 minus 4. So 0 minus 1 is -1. So now I have 3 to the -1. What is 3 to the -1? Then we have to do a little work with our fractions. Does anybody know what that is? Mixed numbers is actually easier. What is it?
3 2/3.
Yep. So this is actually -3 2/3. So it's still crossing between 3 and 4 down here, right? It's just that it's a little bit beneath the value of 3 1/3. So in terms of my y-intercepts, sort of my ordered pair over here, the y-intercept is at x equals 0 and y equals -3 2/3. Was it 2/3? Yeah. My graph doesn't look very accurate on that y-intercept, but it's okay. It's all right. How about my domain? Yeah, the domain is still all real numbers, -∞ to infinity. How about the range? Yep, -4 to infinity, and make sure you're not including that -4. You're using a parenthesis. Because we're getting infinitely close to this dotted line at -4. Yep.
Well, we're not there.
But we're not there. You're exactly right. We're not there.
It's just,
Okay, so one component of this section is about the graphing stuff, right? That's the part we've looked at so far. The next component is going to be on solving some equations and how that looks in this section. And then our last component is going to be about applications and where we actually see this used, like for reals, okay? Like real life stuff. All right, so the next component is solving equations. So this is an example, 6 and 7 are, of exponential equations. And what we want to do when we're working with our exponential equations is get them both to say that same number to a power. So you can see on the left it already says 2 to a power. I'm sorry, your left. It says 2 to a power. But on the other side it doesn't say 2 to a power yet. It says 1/2, right? Okay, so our goal is to get both sides to say 2 raised to a power. Well, the left side already looks like that. It's -2 to a power. Now it's negative, so we'll have to figure that out in a moment, but it's okay. Actually, let's do that first. They're both negative, so we can cancel them. Can we do that okay? All good with that? Multiply by -1 on both sides. So I don't have the negatives anymore. All right. 1/2. 1/2 is 2 to a power. What power?
1, negative 1.
Close.
Negative.
-1. 1/2 is the same as 2 to the -1. Everybody good? Exactly. Once the bases match, they both say 2 to a power. What that means is that the exponents also must match. So the exponents, which are now simply x and -1, have to also be equal, and then the problem is over. So this problem ends very quickly because we are able to get 2 to a power very easily on the one side that it didn't already have it. Sometimes they don't end quite so quickly. Number 7 is an example that they end just a little bit further down the line. Okay. On number 7, you clearly have 2 to a power. It's 2 to the 1 on the right. But 8 to the x is not 2 to the x. I mean, it just isn't. But there is a way to change the number 8 so that it's 2 to a power. 2 cubed, you're right. So I'm going to replace 8 with what it's equal to. Right? 8 is the same thing as 2 cubed. So it's just a substitution or a replacement step. I can replace 8 with 2 cubed. Now it's 2 cubed to the x. So our properties of exponents say I am able to multiply those exponents together. We did that together in intermediate. So this is 2 to the 3x. And over here I have 2 to the 1. This is really my goal. 2 to a power on both sides. And once I get that happening, I can compare the exponents and set them equal. So I'm not canceling out the 2's. That's not what's happening. I know it sort of kind of looks like it, but it isn't. What I'm saying is that if they already match, now it must mean that the exponents match as well. So now I ignore the bases and I only focus on the exponents matching. What do I need to do to get this one solved for x? Yeah, divide by 3. Yes, it is. X equals 1/3. Now let's say for a moment that you wanted to confirm with your calculator that the answers that you're getting are true. So grab your calculator for me. As long as you've got a scientific one, it'll work. We'll just check number 7, although we could go back and check number 6 if you wanted to. We believe that the answer is 1/3. So I want you to type in your calculator in 8, and then however your calculator does it, if you have the same kind I have, it'll have a little caret like this that you have to put in. And put in a parenthesis, 1 divided by 3. That's how mine has it.
It's correct.
And you want to check to make sure that you actually get a 2. And you said it does. You can do the same thing over here, right? You could put in, this started out as -2, so write -2 and put the caret, and then put -1. And you can check to make sure it's equal to -1/2. Okay, so cool, right? You can always know that you got the right answer, even if you're in a testing or a quizzing situation or something that you didn't have it done before, because you can always check that. All right, everybody good? Okay, so part of why we're doing that is because we're going to be able to look at applications, not just in this section, but later on. The application that we're going to look at in this section is compound interest, and there's 2 different types of compound interest equations. Here's the first one. This is the one that you see really used, right? For interest anyway, compound interest. I think we've talked about this in intermediate. Is that true?
Yes.
Did we? Okay. It's like it's been a little bit, but I believe we did. A equals P times 1 plus R over N to the NT. P is the principal, which is the amount of the loan or deposit, right? So it's either the amount you borrow, think borrow for school, borrow for a car, borrow for a house, or it's the amount you put into the savings account, save for school, save for car, save for house, okay? T is the length of the investment. The T has to be in years. So if somebody tells you that the time is 18 months, the first thing you got to do is figure out how many years that is. Okay? R is the annual interest rate. What I remember when I was grading this on your intermediate test is some of you forgetting that part. Right? Leaving 3% as 3 instead of changing it to 0.03. Okay, so it's as a decimal, not a percent. N is the number of times the interest is compounded in a year. Annually means 1. Semi-annually means 2. Yeah. Quarterly means 4. Monthly would mean 12. It would be 12 times a year if something was compounded monthly. A lot of your like savings accounts, things like that at banks are compounded monthly. Some are compounded quarterly, it kind of depends. But you can also find things on occasion that are compounded daily, which would be 365. We're going to ignore leap year, even though we're in one. And then A. A is the amount that you have at the end of whatever time it is. Okay, or maybe it's the amount you've paid at the end of whatever time it is. We'll never forget buying my first house and looking at that amount that we were going to pay if we actually paid that house out in entirety and saying, wow, that's crazy stuff right there. We didn't do that. We didn't stay there that long.
I can't remember.
Okay, are we about ready for an example?
Yes.
Okay, I think we are. Oh, one more equation before that, sorry. Continuously compounded. A equals P e to the RT. We, in all truth, I mean, we're going to do examples like it happens, but it doesn't really work like this with money. Compound interest is not something that's really compounded continuously. However, there are many things within the realm of the sciences that do compound continuously, and I'm sure that you will see that used in your science, chemistry, biology kind of classes as you continue moving on. So this is a much nicer equation, to be honest. P e to the RT. P, R, and T, they're all the same thing as you were. A, P, R, and T are all the same things as they were on the previous slide. E is an approximation at 2.718. If you put E into your calculator, it will give you more of a decimal expansion than that. It's an irrational number. It's actually a representation of something else, but they give it the name E. It's kind of like pi. Pi is really just a ratio of the circumference to the diameter of a circle. That's what it really is, and we give it this fancy name pi. E is the same kind of a thing, okay? So we'll do an example with that so you can see how that equation is used, but understand that it doesn't really get used in finance, but it does get used in science. So here's our example from finance for the other equation that we were using. Suppose you invest $80,000 in 4% annual percentage rate for 20 years. Find the value of the account if the interest is compounded annually, quarterly. We're going to keep going. We're going to do monthly and daily, and then we're going to do continuously. Okay, so
This equation?
no, we're not, because it doesn't say compounded continuously. It says compounded annually and then quarterly. So this probably should have been on a separate slide. I was probably just trying to make use of my slides and not have so many of them.
On the next slide, there's CD.
Yes, that's correct. Yeah, so we'll continue with the other components on CD and E over here. That's true. But the equation, I think, was just what Damaris was asking that we're going to be using for the beginning. The first parts A through D is going to be this equation because it says compounded monthly, quarterly, whatever. Okay, so we're using this equation. All right, so let's actually find some of the values, and I'm just going to list them out. We'll list them up here in the yellow. What is the P value for our problem?
80,000.
That's the 80,000. Very good. What is the R for our problem? 4%, so 0.04, exactly. What is the T for our problem? Nope. 20. Time is 20 years. The N, it's just what you were thinking about, Bailey, is what's going to change. So this varies depending on which problem we're on. So the N in the problem we're on is 1. So most of the equation is going to stay the same from problem to problem to problem, but the N is going to change. So this is A equals, P is 80,000 times 1 plus R is 0.04. The N in this one is 1 raised to the NT, so it's 1 times 20. Now, just a word of caution, your calculator has the propensity to actually screw this up for you if you're not being careful. Some of the calculator operating systems understand order of operations a little bit better than others. I have one that's a little bit of an older operating system and it doesn't do a very good job. My advice to you is simply to figure out what the exponent is and to use that reduced exponent, right? So 1 times 20 is 20. It's just a power of 20, okay? So as you're working this problem, you might be able to enter it straight away from left to right all into your calculator. And if you can, that's great. If not, another possibility, especially if you aren't working with a graphing version of a calculator, but maybe you just have a scientific one, is to work from the inside out. For example, take what's in the parentheses first. So 1 plus 0.04, well, divided by 1. And press enter. If you do that, it's going to give you 1.04 on this problem. Okay? Some of the other ones are going to get messier, but this one's just 1.04. You're going to raise that to a power 20 because exponents happen before multiplication. So raise that to a power 20, and it's going to give you something very ugly.
2.191112314.
Yeah, it's really ugly, right? And we don't want to round it off because if we do, we're going to lose accuracy. So where it is in your calculator right now is that ugly 2.191123143 expression. You're just going to hit it times 80. Exactly. Good job, Kaylee. So we're going to hit times the 80,000 at the very end. And then we're going to round with 2 decimals because it's money. And we're going to put our dollar sign as well. So this is 175,289.85 cents. So, I mean, you didn't do anything with it. You just stuck it in the bank at 4% and you left it there for 20 years and it more than doubled.
Dang, that's
Okay.
What I call getting in the
It'd be
back.
great if inflation didn't cut into that.
Yeah.
So, let's try it now. Let's see what happens when we change how quickly it actually compounds. So that's the only thing we're changing on this particular problem the whole time is the compounding. So it starts out the same. A equals 80,000. 1 plus R, 0.04 over N, but now it says quarterly. What does quarterly mean? 4. Think like 4 quarters in a dollar. There's 4 quarters in a year, right? 4. And it's raised to the 4 times t, which is 20. So, like I said before, my suggestion to avoid any potential for your calculator to mess you up is just to recognize that's 80 and use it like that. So again, I would work from the inside out if you have a scientific calculator. If you have a graphing calculator and you want to work from the left to right, you could do that. So I'm going to do 1 plus 0.04 divided by 4, which is 1.01, you're right. And we're going to raise it to the power of 80 this time.
It's a crap ton of money.
And I've got 2.216715217, right? And then I'm going to multiply times 80,000. That's what I have too, Kaylee. Very good. 177,337 and 22 cents.
I got one.
Is it bigger?
A little.
Okay.
Yes, a little bigger. So what happened to yours, Maxwell?
Yeah, I don't know.
Okay.
Oh, I didn't do it over 4. I did 0.04 over 1. My bad.
Okay.
Oh.
So did you forget that part too, maybe, Abby?
Yeah.
Yeah, it will change it very drastically because we're raising it to a power of 80 now instead of to a power of 20, right?
Yeah.
So that number is going to change substantially if I don't reflect the division by 4 right here as well.
Still a crap ton of money.
Still bigger than it was before. So more compoundings is better. Yes, Madison?
I'm confused with the 4 times 20 comes from. Is it the same as the quarterly? 60,
Yeah, over here the equation has NT. So N is the number of times it compounds in a year. So it compounds in this case quarterly, so 4 different times a year. So at the end of March, at the end of June, at the end of September, and at the end of December, 4 times in a year. And then the 20 is actually the number of years that it does it for.
Okay, thank you.
Yep.
So what I would do first is I
Okay, any questions on those two? Okay, now we're going to do the same thing but monthly. So, which means 12, exactly. So I have my 80,000, and it's 1 plus 0.04 over 12 to the 12 times 20. Yeah, so 12 times 20, we'll figure that out to be the 240. So I have 1 plus 0.04 divided by 12. It's very ugly, actually. It's a repeating decimal. It's 1.0033333333. Yeah. We're going to raise that to a power 240, which gives me 2.222582087. And then we'll multiply that by my 80,000. Is it bigger?
Yeah.
Yeah, not a whole lot, but it is still bigger. 177,806.57. We're going to go down and do daily next. So again, 80,000. 1 plus 0.04 over 365, because we've got it daily now, right? Raised to the 365 times 20. It is. So 7,300 is my exponent. So again, I'm going to work from the inside out. 1 plus 0.04 divided by 365. Raised to the power 7,300. So it's 2.22544338 on mine, and then times my 80 grand. And did it get bigger? Yep, $178,035.47. That was supposed to be a decimal. 47 cents. Make sure you're using dollar signs on those. Okay. Continuously. It's a different equation, right? So it's actually an easier one. A equals P E to the RT. So the 80,000 stays the same at the beginning. E is the number. Your calculator will deal with it just fine. R is your interest rate, 0.04. And T is your time, 20. I would still recommend that you go ahead and multiply the exponent part together. 0.04 times 20 is 0.8. And then you can do 80,000 times e to the 0.8, or you can do e to the 0.8 and then times 80,000.
Is there an E button, or are we putting in the number?
There's an e button.
It should be the second.
She's got a different calculator than yours. Just a second. Let me come find it for you, Damaris.
Did anybody help finding the E?
Second, and then.
Anybody else find the E? Oh, it's the same thing. Got it on three.
I use the units because you need this factor. Like, this will give you decimals every time you go there.
Well, do you need to got it on this one?
How to do what?
From the back of the decimals in front.
Okay, everybody find E? Did you get more? Did the number get any bigger? Really little bit, right? Yeah, so the number got just a tiny bit bigger. On this one, you should have 178,043.27. Little bit bigger. Little bit bigger. All All right, any questions on that?
I did not get the same number either.
Don't understand what?
I did not get the same number either.
Okay, let's look at your calculator. Anybody else not get the same thing? All right, let's check in after class, Kayla. All right, so I would shelf this for a day, right? Focus your attention back into chapter 3. Put this on the shelf, come back to it after the test tomorrow, and then you've got the weekend to do section 4.1.